I want to talk a bit about how temperature and size, and for size I mean like radius or surface area or volume, all of those are going to go up, become larger as the radius gets larger. Temperature and size, how those relate to luminosity. And this is an astronomy course, so we will soon be talking about stars, but first we're going to talk about hot plates and cooking spaghetti, because that might be a little bit more intuitive for people to think through, as you have probably tried to boil water at some point in your life, and you probably have not made a star. So, other thing to note before we get going, I'm going to try to be careful with my wording, and I'm not going to say things like bright or faint unless I make a mistake. I'm talking about luminosity, and luminosity is the rate that a star is giving off energy. It is not whether a given star is going to appear brighter or fainter in my skies when I look at it, because that brightness also involves the distance away. So we're just talking about luminosity, something intrinsic to the star, independent of the distance away. All right, so let's start with part one. Imagine you're comparing the ability of electric hot plates of different sizes and temperatures to fully cook two identical large pots of spaghetti. Note that all the pots are as large as the largest hot plate. So we have two sizes of hot plate, large and small. The shading of each hot plate is used to illustrate its temperature. So the darker the shade of gray, the cooler the temperature of the hot plate. So this is the darkest, that's the coolest, this is the intermediate, and then the lightest is the hottest. All right, question one. For each pair of the hot plates shown below, circle the one that will cook the large pot of spaghetti more quickly. If there is no way to tell for sure, state that explicitly. All right, so in case A, I've got two burners, and one is hotter than the other, and the burners are the same size. So the hotter one is going to cook faster. In case B, I have got two burners at the same temperature, but the one on the left is smaller and the one on the right is larger. And the pot of spaghetti is just as big as the area of the largest burner. So at the same temperature, the larger burner is going to cook the spaghetti faster. Case C, I've got a big hot burner and a small cool burner. So the big hot burner is going to cook quicker. And then in case D, this one is the head scratcher. I have got a smaller, hotter burner versus a larger, cooler burner. And it's not obvious without more information and without actually doing a calculation where you know how much bigger an area and how much hotter in temperature, which of those would actually cook our pot of spaghetti quickest. All right. And we'll be talking about that a bit more in the following questions. All right, if you use two hot plates of the same size, can you assume that the hot plate that can cook a large pot of spaghetti first is at higher temperature? Which lettered example above supports your answer? And yes, if I fix the size, the one that is going to cook fastest is the one that's hottest. And that is illustrated in scenario A. If you use two hot plates of the same temperature, can you assume that the hot plate that can cook a large pot of spaghetti first is larger? Which lettered example above supports your answer? And again, yes, you can assume that. That's what's illustrated in case B. burners are at the same temperature, the larger one is going to cook the spaghetti fastest. Alright, if you use two hot plates of different sizes, can you assume that the hot plate that can cook a large pot of spaghetti first is at a higher temperature? Which lettered example above supports your answer? Before we dive into that, let's visit our two student friends. So two students are discussing their answers to question 4. So in 1D, the hot plate on the left cooks the spaghetti quicker than the one on the right, even though it is smaller. The hot plate's higher temperature is what makes it cook the spaghetti more quickly. Student 2, but the size of the hot plate also plays a part in making it cook fast. If the hot plate on the left were the size of a penny, the spaghetti would take a really long time to cook. I bet that if the size difference were great enough, the one at the lower temperature could cook the spaghetti first. So student 2 is imagining taking the limit that in case D, if this smaller burner were at a high enough temperature, it'd still cook the spaghetti fastest. Then imagine, let's go to the case where it's an even smaller burner. And eventually, as this thing shrinks down to nothing, this guy on the right has eventually got to win. It's just a question of when do they balance out of being higher temperature and smaller area would cook just as fast as lower temperature, higher area. Because at some point, they do have to balance each other out. So, I agree with student 2. Student 1 is incorrect. You can't say that for sure without having more information. So let's go back to our question for 4. If you use two hot plates of different sizes, can you assume that the hot plate that can cook a large pot of spaghetti first is at a higher temperature? And the answer is no. And that is supported by case D. You need to have more information to know the trade-off between higher temperature and smaller size. If the higher temperature is also bigger, then that's obvious. But if the higher temperature is smaller, then you need to have more information before you can make a meaningful statement. All right. Let's move on to the next batch of questions. The time it takes for the spaghetti to cook is determined by the rate at which the hot plate transfers energy to the pot. This rate is related to both the temperature and the size of the hot plate. For stars, the rate at which energy is given off is called luminosity. Similar to the above example, a star's luminosity can be increased by, I can increase the temperature and or increase its surface area or size. The relationship between luminosity, temperature, and size allows us to make comparisons between stars. Question 6. If two hot plates have the same temperature and one cooks a pot of spaghetti more quickly, what can you conclude about the sizes of the hot plate? So at a fixed temperature, bigger plate cooks faster. At least until it's as big as the pot, and then you're just wasting area. Likewise, if two stars have the same surface temperature and one is more luminous, what can you conclude about the sizes of the stars? So the more luminous star is bigger if you know that the temperatures are the same. If two stars have the same surface temperature and are the same size, which star, if either, is more luminous? Explain your reasoning. Well, if they have both the same size, so the same surface area, and the same surface temperature, then they're we're going to have the same luminosity. All right, so now we're going to move on from the cooking part of the class back more squarely into astronomy. If two stars are the same size, but one has a higher surface temperature, which star, if either, is more luminous? Explain your reasoning. So same size, but one is hotter. And we have our relationship to the hottest star is more luminous. All right, so now let's go to our Hertz-Russell diagram, HR diagram. Graph below plots the luminosity of a star on the vertical axis against the star's surface temperature on the horizontal axis. And remember, HR diagrams, temperature goes backwards. So luminosity makes sense. It goes from lower to smaller as you go up. The temperature axis in an HR diagram is backwards. So cooler objects are to the right, hotter objects are to the left. And again, I'm sorry, but that ain't changing. Been doing this for a long time. Astronomers have had a chance to change this, and it has not changed. We're just going to keep this axis going backwards. All right, so this graph is called an HR diagram, so the Hertz-Russell diagram. Use the HR diagram below in the relationship between a star's luminosity, temperature, and size, as described on the previous page, to answer the following questions concerning the stars labeled U through Y. So U, V, W, X, Y. Stars U and V have the same surface temperature. Check. They have the same horizontal coordinate. Given that star U is actually much more luminous than star V, what can you conclude about the size of star U compared to star V? We can conclude that U is bigger in size. That's the only way it could be that much more luminous, is to have more surface area. Therefore, it's a bigger star. Star U has a greater surface temperature than star X. Given that star X is actually just as luminous as star U, what can you conclude about the size of star X compared to star U? Alright, so star X is much cooler on its surface, but yet it has just the same luminosity. That is only possible if X is a big boy. Star X is bigger than star U. Alright, question 12. Based on the information presented in the HR diagram, which star is larger, X or Y? Explain your reasoning. Alright, so star X compared to star Y. X is more luminous but has the same surface temperature as Y. Therefore, X has to be bigger. X is larger than Y. X is more luminous, but same surface temperature as star Y. All right, move my HR diagram up a bit. Question 13. Based on the information presented in the HR diagram, which star is larger, star Y or star V? Okay, so star V is hotter, but it has the same luminosity as star Y. So for Y to make up for being cooler on its surface, it must have a bigger surface area. So which star is larger? Star Y. So Y is larger than V. And we know that because it's the same luminosity, but Y is the cooler star. Question 14. On the HR diagram, draw a Z at the position of a star smaller in size than W, but with the same luminosity. Explain your reasoning. So where I'm going to plop that guy down. So I need to have the same luminosity, but be smaller in size. So to be smaller in size and the same luminosity, I'm going to have to go to a higher temperature, which means I go to the left. So that could be, for example, there, for star Z. And so reasoning, I want same luminosity, but smaller size, therefore higher temperature. And we need to remember that in the HR diagram, temperature increases to the left. All right, last question. It is very difficult to accurately predict how the size of star U will compare to that of star W. So we're thinking about U and W. U is hotter and more luminous. W is cooler and less luminous. So it's very difficult to accurately predict how the size of star U will compare to that of star W without performing some kind of calculation. Explain what makes a comparison of the size of these stars so difficult. And what makes this difficult is I don't know how the size is necessarily going to vary without doing a detailed calculation, because U is the hotter star and is also the more luminous star. It could turn out to actually even be the smaller star. I would need to know how big the difference is in luminosity and a precise knowledge of what the difference in temperature is before I could say something about the size. So it's a combination of temperature and size making U more luminous than we're comparing to star W. All right, and just to remind folks of what that relationship is, the luminosity comes from two parts. There's the part that goes as the surface area of the star, so 4 pi radius squared, and a part that comes from the flux at a given temperature, which is sigma, the Stefan-Boltzmann constant, temperature to the 4th power. All right. So I can get a high luminosity by being a big star. I can get a high luminosity by being a hot star, hot surface temperature.